Come on, my dears, we proceed further in the illustrations of chapter number 1. Kindly read this statement of illustrative numerical number 15. Read it? Look. As shown in the diagram, we have some uniform linear charge distribution placed over a circular arc of radius small r having center at the origin. Okay, fine. Here I am showing the presence of positive point charges, correct, by plus signs. That is how you can consider linear charge distribution of positive point charges over this circular arc. Fine. And now, this entire circular arc makes total angle theta at the center, and that angle is made by this arc with this x-axis. Okay, we will measure that angle anti-clockwise this way. Fine. Now what we are asked to find out here, what is the resultant electric field produced by such a charge distribution at this origin? Let us find out. Just to find out that resultant electric field, you please do one thing. You please divide this circular arc into very large number of extremely small length elements, extremely small length elements. And one such extremely small length element I have shown in the diagram here, having length dl. That length element makes angle phi with positive x-axis, and it makes angle at origin which is very small angle, and let it be d phi. Angle made by this length element with positive x-axis is phi, and angle made by the same length element at origin is d phi. Okay. What was the formula for length of circular arc? I told you to remember in words, radius into angle. Radius is right now r into angle, angle is d phi, right? So length of this length element would be dl equals to radius into angle, that is r into d phi, correct? Now this length is such a small length such that the amount of electric charge contained in it is suppose dq, which you may consider as charge of charge element. And if that charge is extremely small, you may consider it common point charge, correct? The space on which it is located itself is very small, then you may consider it like a point charge. And if it is a point charge, then don't you know the electric field produced by point charge by magnitude, it is k into charge upon distance square. Come on, k into charge, that is the q, upon distance square. Distance of this point from this length element is radius of this circular arc, which is small r, and its a square. K into charge upon distance square, correct? Let us find out now this amount of electric charge in the charge element. Come on, so far linear distribution of electric charge is concerned. Which density should you recall? Linear charge density shown by symbol lambda. After all, it is charge upon length, correct? Charge is dq and respective length is dl, which is r into d phi, correct? Find out dq from here, transfer this. So lambda into r into d phi, lambda into r into d phi, correct? Fine. As I said, magnitude of electric field produced by only single charge element, that magnitude I am showing by symbol dE. Why dE? We will call it partial electric field. Why partial electric field? Because right now we have not considered the entire length, we have considered just very small part of it. That's why I call this dE as partial electric field. And if it is produced by a point charge, it is k into charge upon distance square. K into charge is dq upon distance square is r square. Simple. K as it is. What about dq? Value of dq is lambda r d5. Lambda r d5 upon r square. 1 r is getting cancelled. So now it is k lambda upon r into d phi. Correct? What about direction of this electric field? So for direction of electric field produced by a positive charge is concerned, you must remember it is always away from it. For this positive charge, direction of electric field produced by it at this origin would be away from this, like this. Correct? And in that direction there is partial electric field vector dE. Okay? And now this arrow represents that partial electric field vector dE. You can now resolve it into two mutually perpendicular components. Look, this component plus this component, both of them are mutually perpendicular. Come on, make vector addition. This vector plus this vector will give you this vector. Simple? Come on. Now if this angle is phi, then this also will be phi, because they are vertically opposite angles, they have to be equal. If this is phi, this also will be phi. Now tell me, how to find this component? This is the component which is on x-axis. That's why we just call it x component of dE, and we show it by symbol dEx. dEx. X you must write well below dE, okay, as a suffix. Similarly, this is the component which is parallel to this y-axis. That's why we call it y component, and we show it by symbol dEy. Okay, come on. What is dEx? By formula, don't you know? This is the component which is component of dE but adjacent to phi. Component of dE adjacent to phi will be dE cos phi. dE cos phi. And now this is the component opposite to phi. Component of dE opposite to phi is nothing but dE sin phi. dE sin phi. Correct? Value of dEx is dE cos phi, value of dEy is dE sin phi. Simple. Now let us find out vector dEx. Vector dEx, that is this vector. Okay? Come on. Vector equals to magnitude multiplied by unit vector. Vector equals to magnitude multiplied by unit vector. What about magnitude of this vector? It is dEx and it is dE cos phi. dE cos phi into unit vector. Unit vector in this direction, that is along negative x-axis, it is minus I hat. Minus I hat. Fine. What about value of dE? Value of dE is right now k lambda upon r into d phi. Value of dE is, look here, k lambda upon r into d phi. Correct? Cos phi as it is, minus I hat as it is. Okay, I have simply substituted the value of dE. That's all. Now make vector addition on both the sides. So I am taking integration. Come on. Integration of vector dEx. When you take integration here, you are supposed to take integration here also. So k lambda upon r can be taken out because it is constant, and integration of remaining part. So integration cos phi d phi. Integration cos phi d phi into minus I hat. Don't forget. And so far lower limit of integration is concerned, you must remember it is nothing but smallest value of variable, and upper limit is highest value of variable. Right now you have taken this length element over here, but if you take this length element over here, this angle phi will be 0. Phi will be 0, which is minimum value of phi. And then after you may just change the position of that length element continuously like this, and you may bring it here. When you bring it here, it is the end of the given linear charge distribution, and at that end point value of phi is this much, that is equal to theta, which is maximum. So minimum value of phi is 0, maximum value of phi is theta. Minimum value is the lower limit and maximum value is the upper limit, correct? That's why we should carry out this integration from 0 to theta, from 0 to theta. Now addition, vector addition of x components of partial electric field will give you x component of resultant electric field. X component of resultant electric field, you may show it by this symbol, vector Ex, correct? Now this k lambda upon r as it is, derivative of sine is cos, speak reverse, integration of cos should be sine, integration of cos should be sine. Because it is cos phi, you may write here sine phi, correct? But the limits are from 0 to theta, from 0 to theta, into this minus I hat as it is, correct? Fine. Now this vector Ex as it is, k lambda upon r as it is. Now place the limits. Instead of phi, you are supposed to write the upper limit first, that is theta. So you will write sine theta. After putting minus sign, you are supposed to write the lower limit. That is, instead of 5, you should write 0, that is sine 0, into minus I hat, don't forget. Now sine 0 is 0, so left here in the bracket is sine theta into minus I hat, this k lambda upon r as it is, okay. What is this? Come on, vector Ex, that is x component of resultant electric field, okay. Similarly, let us find out y component of resultant electric field. First of all, start with this vector dEy, vector dEy. Vector equals to magnitude multiplied by unit vector. Magnitude of this is dEy, which is dE sin phi, dE sin phi, and into unit vector. Unit vector in the direction of this vector means unit vector in the direction of negative y-axis, and in the direction of negative y-axis, what is the unit vector? Minus j hat, minus j hat. Take care while putting j, okay. In hurry, you may write like I and the examiner will just read it wrongly, okay. Please write j means j only, okay. Fine. Now dE is how much? dE is, come on, k lambda upon r into d phi, k lambda upon r into d phi, sin phi as it is, minus j hat as it is. And now just make, take integration on both the sides, take integration on both the sides. Integration vector dEy, and that equals to, this part is constant taken out, integration of remaining part, that is integration sin phi d phi into minus j hat, don't forget. But the limits are from 0 to theta, 0 to theta. I just remind, lower limit of integration means the smallest value of variable, which is right now phi minimum equal to 0, and upper limit of the integration is highest value of the variable, which is right now phi maximum equal to theta, phi maximum equal to theta. That's why you should integrate between these limits 0 to theta. Now vector addition of y components of partial electric fields will give you y component of resultant electric field, that is vector Ey, correct. This k lambda upon r as it is. Now derivative of cos is minus sine, speak reverse, integration of sine is minus cos, integration of sine is minus cos. So you should write minus cos phi, because here it is sin phi, then you should write minus cos phi, simple. And then which are the limits? From 0 to theta, from 0 to theta. Don't forget to write in multiplication this minus j hat, okay. Now this part as it is, minus as it is, cos as it is, instead of variable phi, you are supposed to replace it by upper limit, that is theta. Come on, substitute upper limit first, instead of phi you may write theta. After putting minus sign, in the same term, instead of phi you are supposed to write the lower limit, that is 0. So minus cos 0, minus cos 0, and into minus j hat, don't forget. Now cos 0 is 1, minus minus plus, so plus 1 I am writing here, minus cos theta into minus j hat, and this k lambda upon r as it is. What is this? Y component of resultant electric field, fine. Now at this point O, due to entire given charge distribution, the resultant electric field I am taking by symbol vector E. And you know, in 2 dimensions it will have only 2 components, x and y. So you can write vector Ex plus vector Ey. Correct? Fine. Now this vector E as it is. What about vector Ex? Vector Ex, same formula written here, same formula, no change whatsoever. Correct? Plus vector Ey, this vector Ey, same formula written here, no change. Okay. Now which part you can take common? K lambda upon R, K lambda upon R, this much part you can take common. That's why I am taking K lambda upon R out. Inside the bracket, minus sin theta into I hat, minus sin theta into I hat. This K lambda upon R is taken out. Inside you can see here it is minus sign, you may multiply inside, then order will get reversed. Now it will appear cos theta minus 1, cos theta minus 1 into j hat. Correct? Something like something into I hat plus something into j hat. Okay. So this is giving you resultant electric field produced by given linear charge distribution over a circular arc of radius small r having linear charge density as lambda produced at its center, which is right now origin. Correct? Fine. Now kindly read this statement of illustration number 16. Read it? Look. We have one extremely thin circular ring with radius small a and having total positive charge, say capital Q. Okay. What we are asked to find out here, the electric field produced by this ring at some axial point, say point P, which is at distance x on its axis from its center. Okay. How to find out that electric field? I am showing you. Look, first of all, you just select diametrically oppositely located 2 charge elements. Select 2 charge elements which are arranged over the periphery of this ring diametrically opposite. So one such charge element I am showing here, and diametrically oppositely located another charge element is here. Okay. So this we may consider as vertical diameter. Fine. Now due to this charge element, say having charge dq, what is the electric field at this point P? You know, for a positive charge it is always away from it. So away from this it is like this. Fine. And that partial electric field magnitude wise I am showing by symbol dE. Correct? Similarly, the magnitude of electric field produced by this charge at this very point is in this direction, away from it this way. And I say these 2 magnitudes are equal. Why? Because these amounts of electric charge are equal. Not only that, whatever is this distance, same is this distance. So that's why these 2 magnitudes are equal. Fine. Let it be partial electric field shown by symbol dE. Now take this angle as theta, this is also theta. If this is theta, this also will be theta. This is theta, this also will be theta. These 2 are vertically opposite, these 2 are also vertically opposite. Now resolve this vector into 2 mutually perpendicular components, this vector plus this vector. Similarly, you can resolve this also into 2 mutually perpendicular components. Come on, this vector plus this vector. Correct? Come on. Component of dE opposite to theta, it is dE sin theta. Component of dE adjacent to theta is dE cos theta. Similarly, for this component of dE opposite to theta, DE sin theta. Component of DE adjacent to theta is DE cos theta. And now tell me, how to find these two components? They are equal in magnitudes, correct? And opposite in directions, equal in magnitudes, opposite in directions. So naturally they will cancel the effect of each other, and if such sign components are cancelling the effect of each other, then you will get resultant electric field at this axial point only due to such cosine components, that is only due to dE cos theta components, correct? And now to find out resultant electric field at point P, you can simply take scalar addition of such components because they are in the same direction. And whenever vectors are in the same directions, you can make their scalar addition. Okay, that's why when you make scalar addition, that is integration of dE cos theta components, that is summation of dE cos theta components, it will give you magnitude of resultant electric field. Why we are taking scalar addition? Because these components are in the same direction. Okay, first of all, let us find out the magnitude of partial electric field, that is dE. Because it is electric field produced by charge element which can be taken as a point charge, what is the formula? K into charge upon distance square. K into charge is dq, and this distance I am taking as small r. If this distance is small r, then its square I am writing r square, correct? K into dq as it is, but r square. What is this side? For this right angle triangle, what is this side? Opposite to right angle, that is hypotenuse. And according to Pythagoras theorem, what is square of hypotenuse? It is summation of squares of this and this. That is small r square will be a square plus x square. Come on, small r square will be a square plus x square. Simple. And now as I said, integration of dE cos theta will give you magnitude of resultant electric field at this axial point. Okay. Now this closed integration we are taking. Why? You must have come to know. Because these charge elements are located over a closed curve. That's why we should find out closed integration, correct? This closed integration as it is. Now value of dE. Value of dE is how much? K into dq upon a square plus x square. K into dq upon a square plus x square into cos theta. For this right angle triangle, what is cos theta? Adjacent to theta, that is x, upon hypotenuse, which is, come on, according to Pythagoras theorem, measurement of hypotenuse will be, come on, square root of summation of squares of remaining two perpendicular sides. So this hypotenuse will be under root of a square plus x square, under root of a square plus x square. So what is cos theta? Adjacent side to theta, which is x, divided by hypotenuse, which is under root of a square plus x square, under root of a square plus x square, correct? Fine. Now this closed integration as it is, kx as it is, upon a square plus x square whole raised to 1 you can say here, and here whole raised to 1 by 2. Whenever bases are same, you can take addition of powers in multiplication. That's why it is a square plus x square whole raised to 1 plus 1 by 2. 1 plus 1 by 2, that is 3 by 2, correct? And this dq as a variable you must write like this. Okay, fine. For a given axial point, this distance x is constant, correct? X is constant. K is as such constant only. X is constant. For a given circular ring, radius is constant. In short, this part is constant, and because this part is constant, you can take it out of the symbol of integration. So just take this part out, and left is inside the bracket. Now closed integration of dq. Closed integration of dq, correct? Now this part as it is, this part as it is. But tell me, what will this give you? Closed integration of dq means summation of amounts of electric charges contained in all the charge elements which are spread over the circumference of the ring. When you add up all the amounts of electric charges in all the charge elements spread over its circumference, naturally it will give you total charge over the entire ring, and let it be capital Q. As such, it is given in the statement that total charge contained in the ring is capital Q. So this is the giving you total charge on the ring, which is capital Q, correct? So integration, closed integration dq is going to give you total charge on the ring, and it is capital Q. This is capital Q, K as it is, X as it is, denominator also as it is. So what does this give you? Magnitude of resultant electric field, in this case at this axial point P, which is at distance x from the center of the ring on its axis. Okay. K into Q into x upon a square plus x square whole raised to 3 by 2, where small a is the radius of given circular ring. Got it? Fine. What about direction of this electric field? This electric field is due to only such components dE cos theta, correct? And those directions you can see, they are away from this center, correct? That is from O to P, in this direction, away from the center, okay? If the charges present here are negative charges, suppose, then direction of electric field will be reversed like this, that is towards the center, got it? Fine. Can we read now statement of illustration number 17. Read it? Come on. Tell me what is given to us. We are given a square of side length small a, having its one vertex at origin, and the entire square is present in the first quadrant. Okay, fine. Now, over this square, there is non-uniform surface charge distribution given by this formula, sigma equals to sigma 0 xy, where sigma 0 is some constant. X and y are the coordinates of position of surface element chosen on that square. For example, if you select a surface element somewhere here at point P having coordinates x comma y, then that surface element I have shown here for point P. Horizontally this is x coordinate and vertically this is y coordinate. Okay. So far the length and breadth of this surface element is concerned, I have shown in the diagram. This breadth is extremely small increase in the value of x, let it be dx, and this height or this length, it is extremely small increase in the value of y, let it be dy. Okay. What about surface area of this surface element? Let it be dA. Then surface area of this surface element will be something like length into breadth. So you can say dx into dy, correct? For surface charge distribution, come on, which formula you should recall? For surface charge density, sigma equals to dq upon dA. Sigma equals to dq upon dA, that is charge upon area, And just I wanted to make you convinced with the surface charge distribution. That's why in the figure I have not shown simply a square, I have shown the filled up part of the square, that is this part is shown shaded, and the shaded part indicates the presence of point charges distributed continuously over the entire area of the square. Okay, fine. Now this sigma is surface charge density, which is right now given to you in the statement, sigma equals to sigma 0 xy. Sigma equals to sigma 0 xy. This dq as it is. What about dA? dA is the area of given surface element, which is right now length into breadth, that is dx into dy, correct? Now if you want to find out dq, you may transfer this denominator here. So dq will be sigma 0 into x dx into y dy. I repeat, sigma 0 into x dx into y dy. Simple. Now, out of this partial amount of electric charge, if you want total electric charge contained in the entire square, then you should go for finding surface integration. Come on, that surface integration when you take here, you must take it here also, but when you take it on the right hand side, sigma 0 is constant. Okay, then remember, as many variables, that many integrations. As many variables, that many integrations. Here 2 variables, So, two integrations. Come on, integration x dx into again integration y dy, correct? Now tell me, so far lower limit of integration is concerned, it is nothing but smallest value of variable. If you select this surface element over here, then smallest value of variable x will be x equal to 0 at origin. That's why I am putting lower limit 0. When you select the surface element not here but here suppose, then highest value of x is this much, which is equal to side length of the square, that is a. Again here also, what about variable y? When you select this surface element here at origin, value of y is 0. That's why I am putting here 0. But what about highest value of y? When you take surface element here, highest value of y will be this much, that is equal to a. That's why I am putting upper limit as a. Okay. In short, you should integrate both these functions from 0 to a. Got it? Summation of partial amounts of electric charges will give you total electric charge, capital Q. Come on, sigma 0 as it is. Integration x dx means what? X square by 2. Integration x raised to n dx. What was the formula? X raised to n plus 1 upon n plus 1. Similarly, here integration x raised to 1 dx means x raised to 1 plus 1 upon 1 plus 1. That is x square by 2 from 0 to a. Integration y dy by formula, it is y square by 2 from 0 to a. Wait. Here, because it is a square, the side length is same for each side. That's why 0 to a. Suppose in the examination you are given rectangle, not square but rectangle, having length a and breadth b suppose. Then you may take here 0 to a and here 0 to b, mind well. Sigma 0 as it is. In place of x, when you place upper limit, that is a, it will appear a square by 2. After putting minus sign, when you write instead of x, come on 0 upon 2 will be 0. Similarly here, first of all place upper limit, in place of y you must write a square by 2. After putting minus sign, in place of y you should write 0 upon 2, that is 0. Now sigma 0 as it is, a square into a square, a raised to 4 upon 2 to the 4. Tell me, what does this give you? Come on, total amount of electric charge contained on a given square, correct? Where sigma 0 is some constant which appears in this formula. They may give you some numerical formula for this sigma 0. They may give you side length value, and ultimately they may ask the total charge contained in the square in coulomb. You can find it out. Okay, fine. Now read statement for illustrative numerical number 18. Have you read it? Look, we have one electric field which is given in the statement that it is represented by such a formula, vector equals to b into x I hat plus y j hat upon x square plus y square, where b is some constant and x and y, they are x and y coordinates of a point chosen in that region. Okay, fine. Now, we are also given one spherical surface having its center at the origin, having radius small r. And now, when this spherical surface is present in that electric field, what is the electric flux linked with this spherical surface? That is what we have to find out. I am showing you. If that electric field is existing here, and if electric field lines are going this way, correct, say away from this origin, correct, in 2 dimensions, then because electric field is given in 2 dimensions, the electric field lines also will be in 2 dimensions. Okay, fine. And now tell me, in that space, in that region, if you consider this spherical surface, then some electric field lines will be associated with this spherical surface, giving you some amount of electric flux linked with this spherical surface, which we require to find out. Okay, do one thing. First of all, on this spherical surface, you just select a point P having coordinates say x, y, z. because this spherical surface is to be considered in 3 dimensions. That is why it has 3 coordinates. Fine. Now, the position vector of point P with respect to origin or with respect to center of the spherical surface is vector r, and in the same direction I am choosing a unit vector, that is r hat. Okay. What about area vector for this surface element? Area vector is always to be drawn perpendicular to plane of given surface element. Not only that, for a closed surface it must be shown perpendicularly outward. That outward vector I have shown here, vector dA, correct? It is representing surface area vector, which is the area vector for this surface element. Wait, direction of vector dA and direction of vector r, they are in the same direction, and so in the same direction we are choosing one unit vector, which is r hat. Okay, you can take this as unit vector in the direction of vector r also, in the direction of vector dA also, no problem. Now let us find out this unit vector. How will you find out unit vector in the direction of any given vector? Just divide that given vector by its magnitude. Whenever any vector is divided by its magnitude, it will give you unit vector in the same direction. Come on, vector r. Position vector, general expression for position vector of a point in 3 dimensions is x I hat plus y j hat plus z k hat upon r. And now I want electric flux linked with this entire spherical surface, let it be phi, and as per the formula we know it is nothing but surface integration of electric field taken over the surface. Surface integration, that is why I am putting, come on, integration vector E dot vector dA. But because given surface is a closed surface, you must write here closed integration, correct? Mind well, in the figure you may find it like a circle, but you should not, in the mind you should not consider it like a circle, just consider it like a volleyball, that is a spherical surface in 3 dimensions. Okay, fine. And now this is closed surface integration. Okay, there is surface integration as it is. What about vector E formula? They have given in the statement, given by this formula, b into x I hat plus y j hat upon x square plus y square. This formula they have given in the statement. Okay, dot, come on, vector equals to magnitude multiplied by unit vector. Magnitude of vector dA, that is dA, into unit vector. Unit vector in this direction means unit vector in the direction of vector r, and unit vector in the direction of vector r is nothing but r hat. That's why I am putting here r hat. Okay, fine. Now this closed integration as it is, b as it is, this bracketed part also as it is, dot as it is, dA as it is, just simply place the value of r hat. Value of r is right now x I hat plus y j hat plus z k hat upon r. X I hat plus y j hat plus z k hat upon r. Now take care. This closed integration as it is, b into dA upon r, b into dA upon r, I am separating, and now in the denominator it is x square plus y square, that also I am writing as it is. But mind well, this dot product is always to be taken between 2 vectors. Here this part is vectorial part, here this part is vectorial part. Between these 2 vectors you must carry out this dot product. Come on. X into x, that is x square, I hat dot I hat is 1, but I hat dot j hat is 0, I hat dot k hat is also 0. Similarly here, j hat dot I hat 0, j hat dot j hat is 1, y into y, y square, j hat dot k hat is 0. So when you carry out dot product between these 2 vectors, answer is x square plus y square, and divided by in the denominator it is already there, x square plus y square. Numerator and denominator are same, so this ratio is now 1. But here b is constant, and whether you select surface area element here or here or here, anywhere, for a given spherical surface its radius is constant. So b is constant, r is constant. That's why you can take b upon r out of the symbol of this integration, take it out, then left is closed integration of dA, because this part is 1 now, this part is 1. Okay, and what do you mean by closed integration dA? Means summation of areas of all the area elements chosen over given entire surface. When you select such area elements and on the entire spherical surface, and then after when you add up their areas, naturally you should get total surface area of a given sphere. And don't you know surface area of a sphere by formula 4 pi into radius square, 4 pi into radius square, 4 pi into radius is r, its square, and this b upon r as it is, b upon r as it is. Okay. Now one r is getting cancelled, giving you 4 pi b r, 4 pi b r, correct. Please remember this formula in this case, okay, where b is given constant in the expression of electric field and r is the radius of a given spherical surface. They may give you some numerical values for these two quantities. They may ask you to find out electric flux. Okay, fine. Now kindly read the statement of illustration number 19. Have you read it? Look, we have one point charge, say small q, in front of which we have kept one circular disc having radius small a at distance capital R. Now due to the presence of this point charge, what is the total electric flux linked with this circular disc? That is what we have to find out. First of all, try to understand how the electric flux is associated. I am showing you. Surrounding to every charge, it will have its own electric field. And when electric field is there, we can just exhibit that electric field pictorially by taking help of electric field lines. Come on, those electric field lines, because we are showing it for a positive charge, must be shown away from it. Come on. Out of this many number of electric field lines, you can see some electric field lines are going this way, and when they are going this way, they will be incident on this circular disc. That is, this circular disc will have some electric flux, which is what we require to find out. Okay. In textbook they mention that the number of electric field lines is called electric flux. My dears, it is not true. If that number is electric flux, then number has no unit. Number has no unit. Then electric flux also should not have any unit. But electric flux has the unit. It means to say, don't say that number is flux. Don't say like that. When you say that number of electric field lines associated with a given surface is greater, at that time electric flux is greater. If that number is less, then electric flux is less. So electric flux linked with any surface gives you measure of number of electric field lines associated with that surface. That number itself is not electric flux. My dear, please remember. Look here now, we would like to have some exact measure of electric flux linked with this circular disc because of this presence of this amount of electric charge at this much distance. Let us find out. First of all, you do one thing, you divide this entire surface area of the disc into extremely large number of extremely thin concentric circular rings, the way I am showing. Look, you may think of extremely small circular ring at the center like this, which is surrounded by first ring like this, second ring, which is surrounded by third ring, surrounded by fourth ring, and so on, correct? All these rings are concentric, which are extremely thin, each of them having thickness say dr. And one such a specimen circular ring I have shown here as a specimen. Okay, fine. This ring has radius this much, let it be smaller, its thickness is dr. Okay, fine. Now, just take distance of this point at the top of the ring from this charge as x. Okay. Can't you see some right angle triangle here? Come on. This is the right angle triangle. This is the right angle. Opposite to right angle will be hypotenuse. According to Pythagoras theorem, square of hypotenuse will be equal to summation of squares of remaining two perpendicular sides. Come on. X square will be equal to r square plus r square. X square equals to r square plus r square. Mind well, this r is not radius. This capital R is distance of given point charge from the center of the circular disc on its axis. Okay. And this small r is the radius of considered concentric circular ring among many concentric rings on this circular disc. Okay. Come on. Square of hypotenuse will be giving you summation of squares of remaining two perpendicular sides according to Pythagoras theorem. Now take 3 by 2 power on both the sides. Come on, take 3 by 2. Here also, power 3 by 2. So 2 will cancel, giving you x cube. And here when you take 3 by 2, you will get r square plus r square whole raised to 3 by 2. Fine. So this is the value of x cube we will require in the later stage. Okay. Now, just I would like to find out electric flux linked with this considered ring only. With this considered ring only, correct? I am not finding the total electric flux, I am finding part of that total electric flux which is linked with this ring only. That is why we will call it partial electric flux. Partial electric flux. Okay. What was the formula for electric flux? Come on. Electric field into area vector, magnitude of area vector multiplied by cos theta. Magnitude of electric field multiplied by magnitude of area vector multiplied by cos theta. Magnitude of electric field, come on, dE. Magnitude of area vector dA and multiplied by cos theta. Now first of all, think of this dE. What about its direction? I am showing you. Direction of electric field produced by this charge at this very point will be naturally away from this positive charge this way. That's why that electric field I am showing this way in this direction. Great. And it's shown by symbol vector dE. What about vector dA? It is area vector. And have you not remembered, area vector is always to be drawn perpendicular to plane of given area element. Right now area element is in the form of circular ring like this, correct? But its a plane is surface of the disc, and for surface of the disc you can just draw one vector perpendicular to that surface this way. So this is giving you area vector which is perpendicular to the plane of this area element, correct? That is perpendicular to surface of the disc. Correct. And this is direction which is vector dE. This is direction which is vector dA. Come on, angle between them I am taking as theta. If this angle is theta, this also will be theta because they are corresponding angles. These two are parallel. Look, these two are parallel. This is transversal. So these two angles have to be equal. If this is theta, this also will be theta. I repeat. Direction of this electric field is away from this positive point charge this way. Direction of area vector is perpendicular to the surface of the disc like this. Got it? An angle between them I am taking as theta. What about the electric flux value? It is equal to multiplication of magnitude of electric field, come on, magnitude of area vector and cos theta. That is dE into dA into cos theta. What about dE? dE is the electric field produced by this point charge at this much distance which is x. Don't you know magnitude of electric field produced by point charge? K into charge upon distance square. K into charge is Q upon distance square. Square of this, that is x square. What about dA? dA is the area of given area element. Right now area element is this, which is the area of considered specimen ring. And for extremely thin ring, please remember its area in words, circumference into thickness, circumference into thickness. When radius is small r, what about circumference? 2 pi r into thickness. Thickness is this much. Thickness is this much, which is dr. Correct? Come on. Area of extremely thin circular ring is in words. Please remember circumference into thickness. When radius is r, circumference will be 2 pi r. Thickness is dr. In short, value of dA will be 2 pi r dr. Come on, value of dA is 2 pi r dr into cos theta. Take care now. Cos theta in this right angle triangle, which is adjacent side to theta, that is r. divided by hypotenuse, that is opposite to this right angle, which is x, correct? So cos theta is adjacent to theta divided by hypotenuse. Now simplify 2 pi k q r, 2 pi k q r into small r into small dr, into small r into dr as it is, and x into x square, that is x cube. I repeat, 2 pi k q r, 2 pi k q r into r dr divided by x into x square, that is x cube. Fine. Now this part as it is, r dr as it is, but the value of x cube we had found out earlier. Here it is. X cube is how much? R square plus r square whole raised to 3 by 2. R square plus r square whole raised to 3 by 2. Got it? Now take integration on both the sides. So I am taking integration d5, integration d5. But when you take integration here, this part is constant, can be taken out. Can be taken out of the symbol of integration. I am taking it out. Integration of remaining part, that is integration r dr upon r square plus r square whole raised to 3 by 2. Integration r dr upon r square plus r square whole raised to 3 by 2. Come on, from 0 to a, from 0 to a. Why from 0 to a? I told you many times, lower limit of integration means smallest value of variable, and the upper limit of integration means highest value of variable, correct? When you start taking this concentric rings into consideration, if you start from here, exactly at the center of the disc, the minimum radius you can think, which is 0, and then after you can just continuously take bigger and bigger rings into consideration, and at the end you may take the largest circular ring on the periphery of this disc, and that will have radius which is maximum equal to radius of the disc itself. That is, maximum value of r is equal to a. Come on, minimum value is 0, maximum value is a. Minimum value is 0, maximum value is a, correct? Fine. Now summation of partial amounts of electric flux will give you total electric flux, let it be capital phi. This part as it is, integration r upon r square plus r square whole raised to 3 by 2 dr. This sort of integral value you are given in the statement itself in the form of hint, and that value is minus 1 upon under root of capital R square plus small r square. Minus 1 upon under root of capital R square plus small r square, correct? This is the value of this integral which they are given in the statement in the hint, okay? And which are the limits from 0 to a, from 0 to a, correct? Now this part as it is, come on, substitute first of all upper limit, that is in place of this variable small r, we should write upper limit, that is a, minus 1 upon under root of capital R square plus small a square. That is what I have written here. After putting minus sign in the same term, instead of small r you should write 0. That is minus 1 upon under root of r square, minus 1 upon under root of r square. Got it? And now tell me, under root of r square will be r only, minus minus plus, that is positive term I am writing first 1 upon r, and after that minus 1 upon under root of r square plus a square, minus 1 upon under root of r square plus a square, and this outside part as it is 2 pi k q r, 2 pi k q r as it is, okay. Once again I am reminding, this capital R is not radius, it is the distance of given point charge on the axis of given circular disc, okay. So this capital R is distance, not the radius. The small a is the radius of given circular disc. Got it? Fine. So this electric flux will depend on how many factors I am showing you. It will depend on the value of k, that is, it will depend on type of medium in which this charge is present. Secondly, it will depend on its magnitude itself. Then thirdly, it will depend on the distance of that charge from the circular disc on its axis, okay, and it will also depend on the radius of the circular disc taken into consideration, okay. Fine. Kindly read now illustration number 20. Read it. Look, try to understand the physical situation. Here calculation is very simple. We are given two objects having same radius, say small r. One is charged extremely thin charged circular ring, another is chargeless spherical surface. Extremely thin charged circular ring I have shown here, correct? Just to make you convinced with the charged ring, I have shown the presence of positive charges on its periphery, fine. And another object given to us is spherical surface, which is chargeless. That chargeless spherical surface I am showing here, correct? Fine. Mind well, charge is present only on the ring, not on the spherical surface, okay? They both have same radius. And how is this ring inserted into this spherical surface? I am showing you. Think of a spherical surface, okay, in 3 dimensions. You can make it punctured at these two positions, here and here, okay. When you make them punctured, say you are just producing some small hole, and then after this charged ring, you can just pass through that hole this way. And when it comes out here, you can just bend that charged wire circularly and you can just finish one full turn, okay. This is how you can just penetrate that ring, you can just pass it through that spherical surface, okay, fine. Through and through you can just pass it, fine. And now, you can see now, for this spherical surface, this much part of the ring is enclosed. This much part of the ring which are shown with the yellow color, on which I have shown the positive point charges with green color, this much part is enclosed by this spherical surface, correct? Fine. They both have same radius, ring and sphere, they both have same radius. That same radius is small r, but look carefully in the figure and tell me, whose radius is this? This is the radius of this ring, fine. Whose radius is this? It is also radius of this ring. But tell me, whose radius is this? This is the radius of spherical surface. Whose radius is this? This is the radius of this spherical surface. And because both the radii are same, I am writing r, 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 r. But now tell me, whose radius is this? This is the radius of ring also, radius of sphere also. Why don't you say it is a common radius for both the objects, ring as well as spherical surface? Simple, fine. And now tell me, here also r, here also r, here also r. So this is an equilateral triangle having all the three angles equal, each of them being 60 degree. So not only this is 60 degree, this also is 60 degree. Come on, if somebody is asking you what is this total angle, 60 plus 60, that is 120 degree, 120 degree. So the angle made by that part of the circular ring which is inside this spherical surface at the center is 60 plus 60, that is 120 degree, okay. One more thing you must notice, according to the diagram given to us in the statement, you can see the surface of sphere passes through the center of the ring, and similarly the ring passes through the center of the sphere. Surface of spherical body is passing through the center of the ring and ring is passing through the center of the spherical body. Got it? Fine. Now, let us find out the amount of charge contained on that part which is enclosed by this spherical surface. Let us find out this way. Suppose we don't have this spherical surface. No, we don't have, suppose. And we have only this ring. This entire circular ring makes total 360 degree angle at the center. 360 degree angle at the center. At that time, the angle made by that circular arc which makes angles 360 degree at the center is the charge present over the entire ring, and that charge is capital Q. I repeat, if given circular arc makes 360 degree angle at the center, it means you are considering the entire ring. And when you consider entire ring, what is the total charge on the entire ring? Which is capital Q, correct? So if this is the angle made at the center, this must be the charge on that circular arc. But right now, what is the angle made by only this part of the ring at the center? It is 120 degree. So at that time, what is the charge contained on that part? I repeat, for this much angle made at the center, charge present on the circular arc is Q. Then if by a given circular arc angle made at the center is 120 degree, then what is the amount of electric charge contained on that part? Let it be question mark here. Come on, what will be the amount of electric charge now? This into this upon this. This into this upon this. I am writing here 120 degree into Q. 120 degree into Q upon 360 degree. Degree unit will be getting cancelled, and 123s are 360. So it is giving you Q by 3, which gives you amount of electric charge on this much part of the ring which is enclosed by this spherical surface, correct? Let it be small q. So this Q by 3 is amount of electric charge present on that part of the ring which is enclosed by the spherical surface, okay? Now tell me, if enclosed charge is Q, then what is the total electric flux linked with the part which is enclosing this much charge? Come on, according to Gauss' law, what was it? Phi equals to Q upon epsilon 0. Total electric flux linked with a closed surface is equal to ratio of electric charge enclosed by the closed surface to the permittivity of vacuum. Remembered? Fine. Right now, amount of electric charge enclosed by this closed surface is Q by 3. So this small q is right now Q by 3 upon epsilon 0. Okay. Transfer this 3 in the denominator. So it is giving you Q upon 3 into epsilon 0. Q upon 3 into epsilon 0. But what does it give you? Amount of electric flux linked with this closed spherical surface due to the presence of electric charge inside it, which is third part of total charge on the ring, correct? Come on, ultimately phi equals to Q upon 3 epsilon 0. So this is the electric flux in terms of total charge of the ring, got it? Fine. Come on my dears, now kindly read this statement of illustrative numerical number 21. Come on, read it. Look, we have infinitely long uniform linear charge distribution of point charges. So we have infinitely long line of charge, correct? At present we have shown all the point charges to be positive, fine. How is the electric field produced by such an infinitely long line of charge? Remembered? The magnitude of electric field is capital E equals to lambda upon 2 pi epsilon 0 r, where lambda is linear charge density and small r is the perpendicular distance from given line of charge, okay? And what about direction of that electric field? Perpendicular to the line of charge and away from it. Perpendicular to line of charge and away from it, okay? If this line of charge is made up of negative charges, then direction of electric field is towards it, perpendicular and towards the line of charge. Right now it is made up of positive charges, so direction of electric field is perpendicular to line of charge and away from it, got it? Fine. Now in the electric field of this line of charge, we have placed one electric dipole as shown in the diagram, where negative charge is closer to this line of charge and this positive charge is farther from this line of charge, okay? It is so given in the statement that negative charge is closer, fine. Now separation between these two unlike charges of equal magnitude is 2 millimeter, 2 millimeter. But if you convert it into meter, then 2 divided by 1000, that is 0.002, that many meter. Okay. Distance of this negative charge from this line of charge, they have given 2 centimeter. Convert it into meter, 2 upon 100, that is 0.02 meter. 0.02 meter. Let it be R1, that is distance of first charge from this line of charge. Correct? Now tell me, distance of second charge from this line of charge is suppose R2, then that distance would be this much, and this distance is nothing but addition of these two, that is this plus this. When you take this plus this, answer is 0.022, that many meter. 0.022, that many meter. Okay, fine. Now the strength of electric field at the position of this first charge is suppose capital E1, and the electric force exerted on this first charge is suppose F1. Then don't you know, electric force is charge into electric field, charge into electric field. Magnitude of both the charges is same, let it be Q. Charge into electric field I am taking E1. This Q as it is. What about E1? Don't you know formula of E? It is lambda upon 2 pi epsilon 0 R. When you take here in place of E, when you take E1, in place of R you should write R1, because rest of the part is constant. Okay. Similarly, what is the electric force exerted on this positive charge, that is on second charge? Let it be F2. Again it is charge into electric field, Q into E2. Correct? This Q as it is. Instead of E1 when you write E2, now instead of R1 you should write R2. Okay. Now tell me, this line of charge will exert attractive force on this negative charge. Correct? Because this is positive charge and this is negative charge. They will attract each other. So this is the attractive force. Fine. Let it be vector F1. And this line of positive charges will repel this positive charge this way. So this is repulsive Coulombian force vector F2. But here strength of electric field is greater because distance is smaller. This distance is smaller than this distance. So when R1 is less than R2, when R1 is there in the denominator and this R1 is less than R2, naturally F1 will be greater than F2. F1 is greater than F2. This attractive force is greater, that's why I am showing longer arrow here. This repulsive force is smaller, that's why I am showing shorter arrow here. Correct? Because R1 is less than R2, F1 will be greater than F2. Now we are asked to find out resultant Coulombian force exerted on this dipole. Let us find out. Now these forces are arranged along same straight line. Correct? Fine. Whenever the force vectors are aligned along a given straight line, means they are collinear, and for a pair of collinear forces, remember the resultant force is always bigger minus smaller, bigger minus smaller. Bigger force is F1, smaller force is F2, so I am taking bigger minus smaller. Correct? That will give you resultant force. Fine. Here you can see the electric dipole moment for this electric dipole is in this direction, from negative to positive in this direction. Correct? Vector P. It is perpendicular to this line of charge. The direction of electric dipole moment vector is perpendicular to this line of charge. Fine. Now F1 minus F2 means this minus this. Correct? When you take this minus this, it is this minus this. But when you take this minus this, which part you can take common? Q lambda upon 2 pi epsilon 0. Q lambda upon 2 pi epsilon 0. That much part you can take common. Inside the bracket 1 upon R1 minus 1 upon R2. 1 upon R1 minus 1 upon R2. Correct? Now just multiply numerator and denominator by 2. If you do that, when you multiply by 2 here, I have written that 2 here. But when you multiply by 2 here, it will give you 4 pi epsilon 0. But 1 upon 4 pi epsilon 0 is nothing but small k. Remember, whenever the medium is not specified, you should take by default that these two charges are present in vacuum. And for vacuum, don't you know expression of small k? 1 upon 4 pi epsilon 0. That's why in place of 1 upon 4 pi epsilon 0, I am writing small k, correct? This q into lambda as it is, and this bracketed part also as it is. Now just put up all the values, 2 as it is. What about small k? Proportionality constant coming in Coulomb's law for vacuum, its value was 9 into 10 raised to 9 Newton meter square upon Coulomb square. 9 into 10 raised to 9 Newton meter square upon Coulomb square. What about q? Magnitude of either charge in a given electric dipole. They have given 4 into 10 raised to minus 4 Coulomb. What about lambda? Linear charge density in this line of charge. Linear charge density they have given in the statement 2 into 10 raised to minus 8 Coulomb upon meter. And now 1 upon R1. 1 upon R1. R1 is 0.02 meter. R1 is 0.02 meter, correct? Minus, come on, 1 upon R2. R2 is this much. And that R2 value is 0.022. 0.022 that many meter, okay? Simplify, answer is 0.65 and SI unit of force is Newton, correct? But if you want to write in a vector form, then you may write vector equals to magnitude multiplied by unit vector. Come on, vector F equals to its magnitude, you know it is 0.65 into unit vector weight. Whenever forces are collinear, the direction of resultant force is always in the direction of bigger force. And here bigger force is F1. So resultant force also will be in the direction of vector F1. Vector F1 is this way, that is towards negative x-axis. And if it is towards negative x-axis, then unit vector you must write minus I hat, correct? So direction of this force is right now this way, means pointing towards this line of charge, pointing towards the line of charge, okay? But in this situation where you have line of charge made up of positive charges, you have placed this electric dipole on the right hand side. Not only that, its dipole moment vector is towards right hand side this way, correct? In this situation, the direction of resultant force is towards this line of charge and perpendicular to it, okay? Perpendicular to line of charge and towards it. Got it? Fine. Kindly read the statement of numerical illustration number 22. Read it? Look. We have infinitely extended plane of charge having uniform surface charge distribution. Fine. Mind well, this was a line of charge and this is a plane of charge. This has surface charge distribution, okay? This had linear charge distribution. Fine. Now, we have suspended one charged sphere having charge small q with the help of a string from this point of suspension. Naturally, when this plane is made up of positive charges and this sphere also has positive charge, naturally this will repel this. And as this repels this sphere will go this way. And as the sphere moves towards right hand side this way, naturally this angle will keep on increasing. At a particular stage, it so happens that this sphere comes to rest. And when it comes to rest, at that time, what is the maximum value of theta in the equilibrium condition of the sphere? That is what we have to find out. Now tell me, this plane of charge having positive charge has repelled this positive charge by exerting repulsive force this way towards the right hand side. Fine. And that repulsive force is electric force. I am showing by symbol Fe. Correct? Now tell me, this string remains stretched on any linear object which remains under tension. You know, forces due to tension are produced at the two endpoints equal in magnitude and pointing towards each other. So at this very point, the force of tension is like this. At this very point, force of tension is like this, correct? we should consider this tension because right now we are interested in finding out the forces which are exerted on this sphere. Okay. This force is exerted at the point of suspension. This tension force is exerted on this sphere which we should consider. And now tell me, if I say this angle is theta, this also will be theta. Do you agree? These two are common alternate angles, they have to be equal. So if this is theta, this also will be theta. Now resolve this vector into two mutually perpendicular components like this. This vector plus this vector. When you take this vector plus this vector, it will give you this vector. Correct? Now tell me, these two components are mutually perpendicular. Fine. And now, come on, component of t opposite to theta. What is it? T sin theta. Opposite is always sin, adjacent is always cos. Just remember, component of t opposite to theta is t sin theta. Component of t adjacent to theta is t cos theta. Okay. Now the same component which is t sin theta, I just bring it from here to here without a change of magnitude or direction. Come on, without changing magnitude or direction, you bring this component from here to here. So this component is also t sin theta. Got it? Now tell me, on a body of mass m, there is a downward gravitational force which is mass into gravitational acceleration. It is also called weight. Weight of a body means mass into gravitational acceleration. Fine. Weight or gravitational force exerted on this sphere is mg, which is vertically downwards. But now tell me, this sphere is at rest under equilibrium, and so you must say that the forces exerted in opposite directions must have equal magnitudes. For any body which is under equilibrium, if there are so many forces, more than one forces are there, and yet it remains under equilibrium, you must say oppositely directed forces must be having equal magnitudes. So whatever is the force towards left hand side, same must be force towards right hand side. That is t sin theta must be equal to Fe. Come on, t sin theta must be equal to Fe. But what is Fe? Electric force. Electric force is nothing but charge into electric field. Charge into electric field. Correct? This charge q as it is, which is the charge of the sphere, but this is the electric field produced by this plane of charge having infinite extent and having uniform surface charge distribution. Remember, in the theoretical part of this chapter, we had derived the formula for such an electric field. What was that formula? Capital E equals to sigma upon 2 epsilon 0. Sigma upon 2 epsilon 0 equals to sigma upon 2 epsilon 0, where sigma is surface charge density. Okay. And similarly, because the sphere is at rest, you must say whatever is vertically upward force, same must be vertically downward force. Come on, t cos theta must be equal to mg. T cos theta must be equal to mg. Correct? Now just take the ratio. This upon this equals to this upon this. When you take this upon this, t will cancel. Sin theta upon cos theta, that is tan theta. And now when you take this upon this 2 epsilon 0 will be coming down and it will be in multiplication with this mg. So now it is q sigma upon 2 epsilon 0 mg. Q sigma upon 2 epsilon 0 mg. Correct? I want this theta. So just take tan inverse on both the sides. Tan inverse and tan will cancel, giving you theta equals to tan inverse of this part. Tan inverse of q sigma upon 2 epsilon 0 mg. Mind well, in the examination you may be given all these values, correct? And they may ask you to find out this value of theta. Okay.